And the title of the talk is Particle Physics with AMO Methods. Professor Gabrielse, please.
My presentation. Well, it's a great honor to be here in Korea. I've only been here once before and I enjoyed it, and I'm impressed with how well organized this conference is. It's worth remarking that I think one of our chairpersons, Juan Jose, has been applying to host this conference since I think 2000, okay? And finally, he was given the chance, and it's pretty clear as we experience the hospitality that we should have given him the chance many years earlier to do this. So thank you, Juan, and the rest of the committee. I'm going to talk today about particle physics with AMO methods. And it's worth noting that it's 60 years since parity violation was discovered. And Li and Yang made a proposal, and Wu did a measurement that was beautiful. And the talk I'm going to give today is in the spirit of that kind of small-scale experiment to investigate the standard model and to help develop the most fundamental theoretical descriptions. So I call it particle physics. When you do particle physics and you do it at low energies, there are a lot of particle physicists who don't feel that you're part of the community. We use particle physics goals, but we use atomic, molecular, and optical physics methods. And for people who are doing particle physics, the goal is the goal is the same, but they have methods which are very much different because they use high energy machines and crash things together. So the LHC, for example, is at around a TeV of energy, and we tend to be down here in the cryogenic range. So we start measuring energies in degrees Kelvin. It's a very different approach. And I just want to say that in order to facilitate this sort of measurement, this is kind of a commercial, I and some others will be starting next year a Center for Fundamental Physics at Low Energy, which will specialize just in these sorts of experiments. We'll be doing 2 new faculty searches over the next couple of years, so if anyone is interested in either recommending someone or applying, please let me know. Okay, the standard model. The standard model is the great triumph and also the great frustration of modern physics. And let me elaborate what that means. We heard something about that yesterday, so I'll try not to be too redundant. But you saw a picture like this yesterday. The standard model is a set of particles, interactions, and symmetries, okay? And it relies on quantum field theory. So that package we call the standard model. The symmetries are charge conjugation, parity, and time reversal. Parity is the first one that was discovered to be violated. That was the Wu experiment many years ago. Then after she discovered that, then people said, well, CP must be a good symmetry, because before that everyone had thought parity was a good symmetry. That turned out not to be true. And now CPT is the sort of fundamental symmetry of the standard model. But in the end, it's an experimental question, and we have to answer the question experimentally, not theoretically. Now, quantum field theory has built into it a CPT theorem, so if quantum field theory is right, and we don't know how to behave in doing theoretical physics really without it, then CPT is a good symmetry, and Lorentz invariance is a good symmetry. In one of the talks that follows, you'll be hearing a test of Lorentz, an experiment which is the most recent test of Lorentz invariance. And yesterday in Mariana's talk, you heard about the parameterization done by Kostelecki and collaborators, where they said, let's take the standard model Lagrangian and let's add terms which violate Lorentz invariance. And some of those terms that are added violate CPT. They all violate Lorentz invariance. Now, the real question about the standard model is it right? Well, we can never prove that anything is right. We can only fail to prove that it's wrong. And so what we want to do is test its predictions. And AMO methods are actually the most precise way to test at least some of the predictions. We can test its symmetries, and again, AMO methods work well there. If you want to look for new particles directly, that really has to be done at high energy searches, so that's done at places like the LHC now. And interestingly enough, and Mariana went into that, can it predict the universe that we observe? And the answer is no. In fact, the standard model is wrong. More about that in a moment. Now, what's arguably the greatest triumph of the standard model has been demonstrated by an atomic, molecular, and optical physics test. Okay, the standard model's most precise prediction is for the magnetic moment of the electron. And the magnetic moment in an electron, which is a simple system, can only have one vector. So the magnetic moment has to be proportional to the spin, which I've normalized by spin 1/2 by h bar over 2. The dimensions are all in the Bohr magneton. The Bohr magneton is the size of a magnetic moment that you would have if you had a circular motion of a charge and a mass. Okay, and then you just figure out what size magnetic moment that current loop would give you. And then what the standard model predicts and what in fact we measure is the ratio of the magnetic moment to the Bohr magneton, because measurements, of course, always have to be dimensionless in some sense. Okay, this is just the argument I gave you in words, but here's the standard model's most precise prediction. The magnetic moment in Bohr magnetons is equal to this expansion. The first term is from the Dirac equation. The Dirac equation predicts most of the magnetic moment. Quantum electrodynamics, the interaction of electrons and photons, basically, describes this series, and this is the fine structure constant, 1 over 137 over pi, and the series then converges. It's an asymptotic series, so maybe it blows up, but that's at a large number of terms. Okay, and so then what theorists have to do is calculate these coefficients. And to calculate C10, which is the one that you have to go that far in order to agree with the measurements or to have the precision of the measurements, C10 involves tens of thousands of Feynman diagrams, computers to do the Feynman manipulation, and so on. And here's all of the terms. They're mostly known analytically, except at C8 and C10. There's an uncertainty. The error bars in this slide, in the last digits, will be in parentheses. These other coefficients are all exact, except there's a lepton mass ratio that's in there, and you have to put that in experimentally. There's hadronic contributions, which are very important at the current level of accuracy, and the new measurements underway, will actually probe the weak interaction as well. So here's the current experimental measurement of the value normalizing everything to 1, and the error bar is here. And then there's contributions from Dirac and from quantum electrodynamics, okay? And then there's hadronic, and then there's weak interactions. And at the current level of accuracy, okay, we're not probing the weak interaction, but we are probing the hadronic term. And so this is more than a quantum electrodynamics test. It's really a standard model test because there's many different sectors of the standard model that are involved. You need good students and stable funding to do these sorts of measurements. That's one reason we're starting the center. It's very difficult for young people often to get started doing these measurements because the papers don't come out quite as rapidly as in other subdisciplines of physics. The scale is pretty small. I mean, usually there's just a couple of people working on the experiment at one time. Here's the apparatus that we used for the last measurement. We have a new one now that we're using. Okay, and several people, David Haneke and Shannon Fogwell, are both represented. Now, the basic idea of the atomic methods, it's sort of like the NIV diamond, but we've been doing this for some decades. Basically, you can make a homemade atom, a custom atom. And our custom atom is a particle in a pinning trap, okay, a device which is well known to many of you in the audience. And the basic idea is the energy level for an electron in a pinning trap, there's a magnetic field, so we can skip most of the trap details. The basic idea is that the electron has a spin, either spin up or spin down with respect to the magnetic field, and it has a cyclotron motion. And both of these are cooled so much, well, the spin, of course, is intrinsically quantum mechanical, but the cyclotron motion is is cooled so much that we're in the lowest quantum states. So it's a fully quantum measurement in that sense. So the spin flip energy is h bar omega c. That's what happens if we flip the spin by driving from the outside. And the cyclotron energy, a single quantum transition, is h bar omega. If you take the ratio of these two energies, you get that the ratio of the two frequencies that one can measure in this trap is equal to just what the standard model is able to predict. It's mu over the magnetic moment in Bohr magnetons. And so there's nothing in physics that you can measure better than a frequency as, say, a ratio of frequencies. So it's ideal for making a precise measurement. There's all sorts of complications on this that I'm not going to talk about, but here's the lowest energy level. Here's the particle in the trap. So this is the pinning trap. This is about a centimeter, the open cavity. The cavity inside is a right circular cylinder and inhibits spontaneous emission. It was one of the earliest demonstrations, actually, of quantum QED to demonstrate inhibited spontaneous emission. This is a spin flip signal that we see, and this is a one quantum cyclotron motion. So if we sit in one of these two stable ground states, this is spin up and this is spin down, and they have cyclotron states that go up to infinity. So if we sit here, we're stable. We can either drive a cyclotron excitation or we can drive a spin flip and a cyclotron excitation, in which case we spontaneously decay to here. So we measure the two frequencies by seeing at which frequencies that we get more of these quantum jumps. So it's quantum jump spectroscopy, another method familiar in atomic physics these days. Okay, so the most precise determination of the property of an elementary particle is what we do here. It's made possible by AMO methods. You can't do this kind of thing at a big accelerator. There's a custom atom with energy levels that we probe. There's cavity-inhibited spontaneous emission. There's quantum jump spectroscopy, quantum demolition detection, which I haven't talked about, but those signals that I showed you are an example of that. Feedback cooling, sideband cooling, and I could list some others, but these are all familiar methods. And this was the measurement that was done years ago at the University of Washington, and we made two measurements and improved things by almost a factor of 15. So here's the result, lots of digits here. Okay, for the magnetic moment in Bohr magnetons, it's 2.8 parts in 10 to the 13. So to test the standard model's most precise prediction, we made the most precise measurement of the property of an elementary particle. How did the standard model do? Well, it did really well. Here's for those of you who like the digits, they're all written out here, okay? And to about a part in 10 to the 12, which is all the better that you can make a prediction right now. Here's the value of the predicted value, and here's the measurement. They agree within the uncertainties. Now, I should hasten to add that in order to make a prediction from the standard model, since remember that expression depended on the fine structure constant, you have to put in a fine structure constant. And the fine structure constant has been produced by a number of people working together. Here's the definition of the fine structure constant. You can rearrange that by sticking the Rydberg constant in. And if Hinch and Udom measure the Rydberg, and these folks in Orsay, Biraben's group, measure a recoil of an atom, and then there's various mass ratios made at various measurements made at various places, then all of those things together give a fine structure constant. Now, the fine structure constant that you get this way is about a factor of 3 or 4 less precise now than what you can get by assuming the standard model is right and using our measured magnetic moment. Of course, if you do that, then you aren't really testing the standard model, and that's what I'm speaking about right now. Okay, now here's the most precise determination of the fine structure constant. To do that, you have to assume that the standard model prediction is correct. Okay, and if you do that, then here's our measurement with the little error bars, and here's the various other measurements that have been made. Now, some of the classical measurements, quantum Hall and other things, they don't even fit anymore on this graph because their error bars are just so enormous. Okay, so this is now, if you assume that the standard model is correct, then we can provide the most precise fine structure constant with these AMO type methods. Now, here's if you say this is the error bar in alpha, and this can just be arbitrary units, but this will calibrate it. Now the question is, how good is the theory okay, for allowing us to go forward with this. And in 2012, there was a big advance when the 10th order QED was calculated for the first time, a real theoretical tour de force. And so when we made our measurement, then the theory was less precise than the measurement. Now they've improved it, and so if we make a new measurement, which we're in the process of doing right now, then we should be able to use the greatly improved theory to extract a better value of the fine structure constant. That's, of course, assuming the standard model is right. For testing the standard model, we need someone else to measure the fine structure constant independently, accurately enough to do the comparison. Okay, now this measurement also puts a limit on what's called physics beyond the standard model, a kind of unusual phrase that's used a lot these days. Okay, and here's the way. If you measure the magnetic moment in Bohr magnetons, that's again the Dirac term, a quantum electrodynamics term, hadronic and weak terms, and then it can be different because of new physics. Okay, and this new physics term is especially interesting because when this was done with the muon, more about that in a few minutes, okay, this term was not zero. Okay, and so that's the only case that I know of where there's a claim that there's something wrong with the standard model, perhaps, but it's only at the 2.5 or 3 standard deviation level, so it's not really completely established. Okay, now what sort of things can we do? Well, with sort of generic models, you can estimate, for the kind of measurement that we are able to do. You can put it in terms of the binding energy of the electron. So if there are constituents inside of the electron, okay, what mass would these constituents have, okay, if they were all sitting out on the table by themselves and not bound together? So how much binding energy? And this is an argument made by Brodsky and Drell, but it's kind of generic, okay? Basically, this mass of all these particles, if we're limited by the current uncertainty in alpha, we can make a limit that this mass is 360 GeV over c squared. Okay, that's a lot of binding energy for a half MeV particle. And if our uncertainty was the only limit, we're actually probing at the TeV scale. Now, in LEP, there were electron-positron colliders. Then a somewhat higher limit of 10 TeV was established by a LEP-Contact interaction limit. That means that the electron is a really strange particle. It has, if there are ingredients in the electron, it has at least 20 million times the binding energy compared to its rest energy, which is really very unusual. Now, can we check the 2.5 or 3 sigma disagreement between the muon magnetic moment measurement and the calculation? The answer is it's going to be a little tricky. Here's how the argument goes. The muon measurement is less precise than ours by about 2,500. Of course, they're trying to improve it by a factor of 3 or 10 or something like that by spending lots of money at Fermilab these days. Maybe you followed the story of the ring being shipped from the East Coast to the Midwest. It was kind of interesting. But why measure the muon if it's so much less precise? The reason is that this term is expected to be about 40,000 times more sensitive to new physics, new particles, for example. And that's the good news. The bad news is that the hadronic contribution is also 40,000 times bigger. Okay, that's bad news because understanding hadronic physics is quite difficult still. Okay, but now they've done a careful job of this, and there's still a 2.5, 3 sigma disagreement. Now the question is, could we improve the electron experiment and actually probe this? Now, 40,000 is a big factor of improvement to do, but since our uncertainty is already 2,500 times better, okay, and a 2 sigma or 3 sigma standard deviation is seen, it means that if we could measure 8 times more precisely, and we think we can do that, we're right now going for a factor of 10, we should be starting to see the new physics if indeed it exists. Now, having said that, there's a big provision here. The quantum electrodynamics and standard model calculations have to be improved slightly, but I think that's not a problem right now because that's being done. The big problem is that one of you has to measure the fine structure constant 20 times more precisely using a method that's different than the one that we're using. And these are large numbers, so unless someone has a good idea, and hopefully someone will, that's still distant. Okay, one last thing is, since people are spending so much effort trying to measure the muon magnetic moment, they're doing that with a large storage ring that's about the size of this room, a little bit smaller, I guess. And the question is, could you do this in a particle trap? And I'll just throw that out. I actually think that one could do it in a particle trap and do it much cheaper. The muon lifetime is, of course, a challenge, but I think there's ways to do it. I haven't started to do it because I already work at CERN and in the United States, and I don't see how I can work on one more continent and keep my life together. But if someone's interested in an interesting project, I at least think it could be done. Now, measurements underway right now. We're trying to measure a positron magnetic moment. We've succeeded recently in loading positrons from a student source that requires no licensing. That's important in a university environment. We think we can improve the best, what's already the best lepton CPT test by a factor of 20 to 200. A factor of 20 just achieving our existing electron precision, and 200 if we improve by a factor of 10. And measuring the electron magnetic moment 10 times more precisely is our second goal. And the new idea there, you can't make a factor of 10 just by working harder. What we want to do is we want to drive those two transitions simultaneously. And if we drive the spin flip and the cyclotron transition simultaneously, then when the magnetic field drifts during the course of a measurement, it'll drift exactly the same for both systems. Okay, if we succeed in doing that, we will start probing the weak interaction effects, and we can determine the fine structure constant 10 times more precisely still, provided that you assume that the standard model is correct. Here's the current team and their trap. There's an apparatus that's working. It has positrons in it right now. It's an entirely new apparatus, which has taken us much longer than I had hoped to get going. We needed the new apparatus in order to get antiprotons in and to solve some technical drift problems that we were having before. But what I learned when we set up a new apparatus is these experiments that we had set up over many years are much more complicated to tune than what one realizes when one does it over years. And it's taking us a longer time. Okay, we'll be probing in the weak interaction term just barely if we get the factor of 10. Okay, now the standard model then works incredibly well. Okay, it can make a prediction which is right to parts in 10 to the 12. Okay, maybe we'll find some place where it breaks down later, but despite the great the success of the standard model can't be the whole story. Okay, in fact, the standard model is wrong in some sense, right? Because it has a loophole in it that you can drive a whole universe through. You can't explain with the standard model, as we heard yesterday, we can't explain how a matter universe exists, because there should have been equal amounts of matter and antimatter created in a Big Bang. As the universe cooled, that would have annihilated. Gravity doesn't fit well in the standard model. You can't renormalize it. You can't explain inflation. Okay, and you can't explain dark energy. And one of the talks in this session is going to be an attempt to use low energy measurements to look at least one very specific model of dark energy. So the standard model, even though it can make wonderful predictions, so it's a great success, it's also a great frustration, because we know it's wrong, and in our laboratory measurements, small and large-scale laboratories so far, we have yet to find, except for the muon, any hint of the breakdown of the standard model. Okay, so this was discussed yesterday about the universe. I won't go into that. I'll just say one of the things you can do in low-energy physics is to do small-scale tests of symmetries of the standard model. Okay, and I already mentioned comparing the positron and the electron magnetic moment. I'll just give you some examples that I'm involved in. You can compare the Q charge and mass ratio of the antiproton and proton. We did that first to better than parts in 10 to the 10. Okay, many years ago. That's recently been reproduced by others at about the same precision. You can compare proton and antiproton gravity. We were able to show that the gravity for antiproton and proton should be about the same to parts in 10 to the 6. And you can compare the antiproton and proton magnetic moments. These are very recent measurements. And I'll say a few things about comparing hydrogen and antihydrogen, because a number of people have asked me about that. Okay, so let me just go to some of these. This is an example, the fourth example I gave, comparing the antiproton and proton magnetic moments. Let me say that that's harder than comparing the electron and positron in some ways, because the magnetic moment of a nucleon is in nuclear magnetons, and these magnetons scale inversely as the mass. Okay, so the nuclear magneton compared to the Bohr magneton goes as the electron to the proton mass, which is roughly 1 in 2,000. That makes it much more difficult to do the measurement. Here's a trap that we used, and the particles actually ended up in here. The distinguishing feature of this trap is basically that we put a huge magnetic gradient, Teslas per couple of millimeters, okay, in order to get the detection sensitivity we need. And so that means that when you do the precise parts of the measurement, you have to do the experiment here and do the detection here. So excitations here and detections here. This is something that our competitors at Mainz and at the base collaboration at CERN now are doing as well. Okay, we made a measurement a couple of years ago, the first in a long time, to improve on the accuracy. Here's the precision of which the antiproton and proton magnetic moments were compared, and we improved, by about a factor of 680. But 680 only takes us into the part per million regime. I don't think that's especially interesting yet. What's really exciting about this is not that there was an initial first step, but as we use the quantum methods, the sorts of things we use for the electron, then hopefully we can improve by another factor of 1,000 or 10,000, and we're busy working at that. Here's an example that we demonstrated that we could actually see individual spin flips of an antiproton, despite the fact that they're of a proton, rather. We did the demonstration with protons, but we demonstrated that we could see them despite the fact that it's sort of 2,000 times, you have 2,000 times less sensitivity. Okay, now comparing antihydrogen and hydrogen, people have been asking me about it, so I'm just going to say a couple of things, even though there's no really scientifically interesting measurements done with antihydrogen and hydrogen comparisons yet. It's been a long and very challenging road. I won't say how many years, but let's say decades are the right unit. Okay, we had to start by actually learning to trap antiprotons, electron-cool antiprotons, evaporative and adiabatically cool antiprotons. Now, these are common AMO methods in some sense, but doing them with an exotic species like an antiproton has some challenges. We had to produce antihydrogen in a nested penny trap. I mean, I demonstrated, you heard Hess's talk about the same time he was proposing to use a trap for Bose-Einstein condensation. We were proposing for a quite different reason to use such a trap in order to trap antihydrogen atoms so they wouldn't annihilate. Very different motivations. There's two collaborations now, my A-trap collaboration and also the alpha trap collaboration, that have trapped antihydrogen. Okay, the next step is to do laser cooling to get the atoms sort of concentrated enough that one has a hope of doing laser spectroscopy, which is the ultimate goal. So the difference with hydrogen is sort of striking, okay? With hydrogen atoms, you hook up a gas bottle, and you have, I don't know, 10 to the 12th atoms or something per cubic centimeter. I forget the exact exponent, but it's a lot. The most we get per trial so far is 5 atoms per trial. Okay, and that really changes your detection sensitivity. Okay, in order to detect that we have trap particles, though, we profit from the fact that if we remove the trap and let the antiprotons out of the trap, they hit a wall and they annihilate, and we have very high detection efficiency for detecting such annihilation. Okay, and so basically, if we do it fast enough, we can do it between cosmic ray counts that are background counts on the big scintillator paddles that we use outside our apparatus to do the detection. Okay, we have a second generation Yaffe trap in place now, but there's things that you hear about, pinch coils, bucking coils, quadrupole, and we also use octupole configurations, okay? And again, the alpha collaboration does much the same thing. And what's a little challenging here is, at least in our case, the electrodes are not at room temperature where you can get out and work at them. They're down at about 1 Kelvin, okay? And so you have a 4 Kelvin superconducting coil to get the deepest possible trap. You have to put hundreds of amps through it, okay, many hundreds in fact, and that all has to be done within a millimeter or so of these a very low temperature cryogenic systems. So there's a lot of technological challenges here. Okay, the coils in our new trap work very well. We can turn them on. This is an example of turning it on in 10 seconds. This was important because our first generation trap, during the time that we turned it on, the strong gradient, which was 10 minutes, okay, because it was a high inductance winding, during the time we turned it on, we watched antiprotons and positrons leaving the trap, and we had a very difficult time getting them together to scale up our antihydrogen production. Now we can turn it on in 10 seconds rather than 10 minutes. We're hopeful that that's going to allow us to get more antihydrogen atoms. Just a curiosity, when we turn off the trap, which we do very rapidly in tens of milliseconds now, okay, all that current has to be dumped outside the apparatus, or of course the cryogenic system will be deeply unhappy. But when we turn it off, the eddy currents induced in our electrodes are enough to heat up their temperature by several degrees. Okay, and so that's bad because it affects the cryogenic vacuum that we have in the trap. So these sorts of problems we're dealing with. Right now, we've observed 600 nanowatts of 121 nanometer light through a system that we produced. This is a collaboration with Dylan Yost and Sue Ali and their students, okay, and some people from our group, okay, and basically this is a system we had at CERN, and we're putting it together. If everything goes exactly right, we may be able to try some laser cooling yet this year, but everything has to work perfectly. Comparing to previous, 600 nanowatts doesn't seem like so much, but 121 nanometers is a little challenging. Compared to previous examples some time ago, it's a bit above, but we think we can get, we've not done any phase matching in our mixing cell, krypton-argon mixture, and so this is at an earlier stage, and so we're very hopeful that we're going to improve this quite a bit. And it should be enough to cool trapped antihydrogen atoms because you get many passes at the trapped antihydrogen atoms. Now, a change of direction. Another type of place that low-energy experimenters like ours using AMO methods, like us, using AMO methods can make a contribution to particle physics is in some cases when the standard model and models made to improve it disagree in their predictions, okay? And then if you can use AMO methods that are sensitive enough, you can sometimes see if you know, who's right. And the electron's electric dipole moment is one example of that. Now, I already talked about the magnetic dipole moment. I can make an exact same argument that the electric dipole moment, if it exists, should be proportional to the spin. This is a large and well-measured value, as I told you earlier. The question is, does it exist at all? Is it non-zero? Okay? And in order to get an electric dipole moment, you have to violate both P and T symmetry. Okay, these days T symmetry is especially interesting because parity violations are relatively more common. Now, the standard model is a delicately balanced system. It predicts a non-zero electric dipole moment of the electron. That means that the charge distribution is squished a little bit. Okay, but it's highly suppressed because you have to go to a fourth order perturbation theory in order to couple in the CP violation that you need to get the T violation that's required. And so basically the standard model predicts that the dipole is on the order of 10 to the minus 38 electron centimeters. We don't have a natural scale for this, and so this is the sort of clumsy unit. Electron charges times centimeters. Now, this is too small to measure by orders of magnitude. The best measurement before we started was on the order of 10 to the minus 27, so this is orders of magnitude away. I won't go into some of the particle physics that explains this. But now extensions to the standard model, the one you've heard most about are supersymmetric models, where there's not only the particles we've discovered, there's also the particles we haven't discovered. Okay, and people at the LHC are working very hard to try and discover these particles, and they have had some candidates, but they seem to be going away from what I've heard, but there's no announcement yet, and so whether or not we'll see them. But they're probing in the TeV kind of range right now, and the idea is that the particles must have a mass that's bigger than our ability to create it, and that's why we haven't seen it yet. And so there's still a lot of hope, and I join that hope, that the LHC does discover such particles. Now, our Acme collaboration it uses AMO methods. It's a joint research effort of 3 research groups. There's John Doyle, David DeMille, who's here and talking later in the week, and myself. And we've had some really good students. A number of them have gotten their PhDs working on this measurement. And we made a 12 times more sensitive measurement of the electron EDM. And the basic idea of such a measurement is that you have to have a Hamiltonian to give you some sort of energy or energy shift. And if the electric dipole moment is very small, you better have an electric field or an effective electric field, which is very big. So the bigger, the better, given that this has been an elusive goal for some years to find this. Now, the electric field would accelerate an electron right out of the apparatus, so instead of doing that, we use the electric field within an atom or within a molecule, though there's an effort at Gilla by Junier and Eric Cornell to do it with a positive ion, but they're also really using a molecular ion, and that's the basic idea. Okay, now the shift theorem said, well, that's not going to work if you just have rearrangements of your charges. I won't go through all this. Sanders pointed out that, in fact, there was an effective electric field that was much bigger, okay? If you had a heavy nucleus and the electron went accelerating around the nucleus, you could actually get a big enhancement of the effect. Okay, and then Cummins and Jackson and DeMille pointed out that you could view this as a Lorentz contraction of the electron EDM in the lab frame. Okay, there's a number of molecules which are promising. Imperial College, Ed Hines is using YBF. At Gilla, they're using this hafnium fluoride, and at Harvard, our Harvard-Yale combination, we're using THO. The effective electric field, in our case, is enormous. It's 100 gigavolts per centimeter, and we can orient that by changing a volt per centimeter electric field in the lab. We use about 100 volts or so and vary it to make sure there's no systematic. Okay, and so we have control then of an enormous field. Our molecule is really special. It has an omega doublet in it. For people like me who don't like molecules so much, it's a 2-level system, and in the effective electric field, if there's an electric dipole moment on the electron, one level will go up and one level will go down. It turns out that there's another set of levels that we can access by just retuning our lasers, which have much the same properties, but the internal electric field is reversed compared to the external electric field in that pair of states compared to the first. That's an important source of systematic rejection. The molecule, the metastable state that we use, also has a tiny magnetic moment. It's 0.01 Bohr magnetons, which is good because then the magnetic field fluctuations make less of an effect. Now, nonetheless, the energy level splitting is very small. It's 2 millihertz, okay? And in high energy physics units, that's a lot of TeV, but in our units, as AMO physicists, it's 7 times 10 to the minus 18 TeV. So we can't resolve it directly. So we do what every atomic physicist would do. We do an interference experiment. We make a linear superposition of the two states, and we can control the phase relationship between them. You have to have a coherent superposition, not a coherent state, a coherent superposition. We let it evolve in time in an electric and a magnetic field, and then the two levels evolve differently because there's a little different energy, okay? And then we read it out using, we prepare and read out by using linear polarized lasers to excite another level and look at fluorescence, for example, that comes out. I don't have time to go into that, but the phase that we measure in this interference experiment goes as the magnetic moment times the magnetic field and the electric moment times the electric field. Okay, here's the parameters that we have. And basically, you ablate the molecules in here. This is a specialty of the Doyle group. Okay, and then basically we have a beam, and then in this region we have an electric field plate, and there's an electric field and a magnetic field. We prepare with there's lots of lasers in this experiment, but I don't have time to go into that, and then we detect on the other end. We get wonderful fringes, okay, so that what we can do is reverse the electric field and see if the phase that we're measuring changes. That's the basic idea of the measurement. One advantage we have is that we can do very fast switches of directions of things, the magnetic field and the electric field, and that gives us a chance to take our data much more rapidly than others, okay? And now the effective electric field in the molecule has to be calculated. There's been various numbers that have come out from calculations that are quite different. For our purposes, these all agree pretty well, okay? And so that's known well enough for this sort of measurement. When we did our measurement, it was blind, and when we unblinded, we found that we too had set a limit on the electric dipole moment rather than observing one that would be of the size that could be predicted with the, from the various models, extensions to the standard model. And to compare, in 2002, the Cummings limit was 1.6 times 10 to the minus 27. Ed Hines did the first molecule experiment, which was an important step, and that's at 1 times 10 to the minus 27 centimeters, and then we went to 8.7 times 10 to the minus 29. So it's a factor of 12 improvement in our measurement. Okay, I don't talk about that. In particle physics terms, a particle physicist would say that, I won't go through the details of this, but we're probing at the 1 to 3 TeV level, okay, which is not so bad for an experiment that's done at very low temperature. At least the beam is at very low temperature. Here's lots of models that have been proposed. We've now moved the limit out here, okay, and some of these models are really hard to stay with, okay? Some of them are going to be almost impossible to eliminate experimentally, but maybe we'll discover the EDM with our next order of magnitude. A couple of things to say. We're going for an order of magnitude right now. We've just published a paper where we demonstrated STIRAP excitation, okay, and I don't have time for the details of this, but that gave us a factor of 12 improvement in molecule flux. We have other small improvements that are sort of straightforward, but the bottom line is we're now almost ready to take data, okay, with a factor of 500 improvement. Statistically, taking the square root, that should give us about a factor of 20, and so we'll see what happens. Okay, there are other measurements. I'll conclude with that. The Imperial College people are also taking data, and Ed told me that they're hoping to improve on our current result by a factor of 4 or so, at least in their first step. And Jilla is trying with a molecular ion, no measurement yet, but they're investigating the systematic effects. There's Penn State and University of Texas Austin measurements that have lofty aspirations. These experiments take a long time. Okay, I think I'll quit now with this. Still no particle EDM has been detected. Okay, here's the proton, neutron, and electron EDMs. There's a new mercury measurement that just came out that I didn't have time to talk about. But the point here is that there is a space where we in the AMO community can use our methods to really try and answer some of the most fundamental questions in physics. I find it's a lot of fun, and I hope that some of you join us in the quest.
Thank you. So we have time for 1 or 2 questions, please. Any questions? Oh, yes, Gordon, yeah. Yes, please.
Say a little more about proton-antiproton gravity comparison.
Yeah, the proton-antiproton gravity experiment, what we did is we compared the cyclotron frequencies of a proton and an antiproton. And that was basically, we did that initially because it was as a CPT test, right, to see if they were the same. That was, the precision we got was 9 parts in 10 to the 11. Now, if you take a clock, okay, I'm switching now. That's our clock. But if you take any clock and you raise it in the gravitational potential, it's well known you get a gravitational redshift. Okay, people have put clocks on airplanes and demonstrated this, but okay, the GPS system, you have to do corrections or we'd be in the wrong place all the time these days, okay? Because those are important corrections. Okay, so that's a well-known thing. Now, if you take a clock and you move it, that's one way of changing the gravitational potential. Another way of changing the gravitational potential is to change the matter clock into an antimatter clock. If the gravity is different for the two, then you will change the gravitational redshift. Okay, so by looking at that limit, that we could then interpret our limit then as placing a limit on how big that, gravitational redshift could be, okay, and then hence on what the acceleration due to gravity for the antiproton and proton. And that limit came at a part in 10 to the 6.
Okay, so we can take just one more question. Yes, Gordon, yes, please. Yes.
Jerry, for the case of the G-2 measurement for the muon, of course, it has a finite lifetime. And also it's interesting because it decays into something else and yet still doesn't seem to have any internal structure. But does the finite lifetime, does that provide a further limitation on the experiment?
Oh, of course. I first thought about this years ago, and this was before the Brookhaven experiment was done, on the muon. And people heard about it, and a representative of the collaboration flew out because they were worried that we were going to do it. And I first decided that, jeepers, we couldn't do it because that lifetime was going to give us such a line width, okay, that I didn't think we could split the line that much, and I sort of abandoned it. Then I started thinking, that lifetime's not so different in high energy physics, okay? And so I went to the collaboration and I asked them about, the line splitting, and first no one would talk to me, okay? They said, we aren't doing line splitting, we're fitting the wiggles, the famous ones from the textbook. So I went to Vernon Hughes, who was headed the experiment, and I said, Vernon, you certainly understand line splitting, what's going on here? And he said in his low voice, well, I used to talk about line splitting to my collaborators. It made them very unhappy, so I don't anymore. Okay, but they have to do the line splitting as well, and there's a lot of line splitting to be done, okay? Now, that means, of course, as you know very well, that you have to understand what's going on down in the wings, not just what's on top of the flat plateau. Nonetheless, I think it is a pretty clean system. I think there are ways that one could have a good crack at doing that, and I think one could even do it in a trap. You couldn't use the kind of methods that our group usually uses. You'd have to use destructive methods because you have to do it fast compared to the microseconds or whatever lifetime there is. But I think it's not eliminated because right now they're making copious amounts of very slow muons, okay, in Japan. And what we could do is you could cool by attrition, which is to say you don't cool at all because you don't have time, right? And so you just have enough of them at low energy that you select the very low energy ones in a shallow well and you use them very quickly. Now, I don't promise it can be done, but if I were 3 decades younger, I think I would find it irresistible to make a crack at it. So, yeah. Mm-hmm.
Okay, so let's thank Professor Gabrielse for a very interesting talk. Okay. The next speaker is Dmitry Budka from Helmholtz Institute, Mainz, and University of California, Berkeley. The title of his talk is Searching for Ultralight Dark Matter with Atomic Spectroscopy and Magnetic Resonance.